Thank you. Thank you for having me. And my session is called Kubernetes and Checkpoint Restore. I'm at Red Hat since 2015 in the core kernel team there, and I'm looking at process migration, which is the basis for container migration, container checkpoint restore, at least for now 12 years. Everything I'm talking about today is about CRIU. CRIU is a tool, it's called Checkpoint Restore in Userspace, which does the checkpointing and restoring of the processes in the container. And I'm involved in CRIU, that's probably since 2012. And since I'm at Red Hat, I'm mainly looking at migrating containers. Before being at Red Hat, I was doing checkpoint restore in high performance computing environments, using it there. So today's agenda is I just want to give a bit background, high-level background about checkpoint restore, CRIU, where it exists and where it came from. Then I want to show a couple of use cases, why you would want to checkpoint restore containers, migrate them, with a couple of demos included there. Then I want to talk about technical details, how CRIU enables us to checkpoint and restore containers. And then I want to talk about the future of checkpoint restore in especially in Kubernetes, what might be coming next. When I wrote the abstract a couple of months ago for the conference, I wrote that now the checkpoint restore or the checkpointing is available in Kubernetes 1.24, and unfortunately this was not has not become true. The process in Kubernetes to get something into Kubernetes is you have to write the Kubernetes enhancement proposal, and then there's a long discussion around it if the new feature should be a part of Kubernetes or not. And I made it, and at the time I wrote the proposal, the Kubernetes enhancement proposal was merged for 1.24, and the assumption was if the cap is merged, the corresponding code pull request will also be merged. Unfortunately, in the last minute, it wasn't merged, but now for the next Kubernetes release 1.25, checkpointing containers is actually possible. The pull request was merged last week, and the demo I'm showing today now uses code which is officially merged in Kubernetes. So it's not longer just a pull request, it's actually part of Kubernetes as of last Thursday. So checkpoint restore in Userspace CRIU, this is the tool which everything I'm talking about today is based on, and the name in Userspace has a reason. Once because it's happening in Userspace, but there's also a reason of the history about checkpoint restore in Linux. Checkpointing restoring processes is something which is a topic in many operating systems for a long time ago, and so it started to appear in Linux maybe, I don't know, 20 years ago. People started to checkpoint restore processes. And at the time, the main focus for checkpoint restore was actually, I think, high performance computing. So you have a really long running job on thousands of nodes, and if one fails, all your computation time is gone, and so you try to create fault tolerance using checkpoint restore. And at that time, there were at least two implementations I know of, and one is a combination of a kernel module, which was never upstreamed, and there was also always some library preloading involved. So in checkpoint restore speak, you would say it was never really completely transparent. So you were not able to checkpoint any process you wanted. You had to prepare it before, and to get to a really transparent checkpoint restore implementation in Linux, there was then maybe 2006 or 7, there was an approach coming which was all based in the kernel, and looking at it from today, it would still be the best solution if it would be all in the kernel, because the kernel knows all the details about the process, so it would be much easier to have it in the kernel. But when this checkpoint restore in the kernel was proposed, it was a really large patch set, like 100 patches, touching a lot of subsystems. And so the community, the Linux community at the time, was not willing to merge this in-kernel approach. So the next approach was checkpoint restore on Userspace CRIU, and that's why it has the name in Userspace, because the previous was in-kernel, and this one is now in Userspace. I will give more details how it works in Userspace to checkpoint and restore process and in the later part of the presentation. So there are multiple integrations of CRIU in different container engines, container runtimes. And the first one to mention is OpenVZ. The company, the group behind OpenVZ, they provide, I think it's called system containers, a thing like this. And they wanted to migrate the system containers like VMs. So they had different approaches to migrate containers, and they wanted a solution which is accepted by upstream, and so they came up with CRIU. And so the big difference of CRIU to checkpoint restore is that CRIU was invented for containers and not for high performance computing as all the solutions before. And that's why we can use today to migrate containers with CRIU really good, because it was designed for this. And so they use it for a couple of years now to migrate containers, and they also invented it. The other big user of CRIU we know of, as from the CRIU community at least, is Borg. Borg is Google's container engine, and there were a couple of conferences. I think they started to talk about it in 2017. So what I know about CRIU integration in Borg is all what I heard at a couple of Linux Plumbers conferences a couple of years ago. So Google decided they want to migrate their containers in production, and they are using it to migrate long-running background tasks. So if there are not enough resources on your node, and for high priority tasks, then the background tasks used to be just killed, and the work was lost, and now they just migrate the long-running background tasks from one system to another system. The example they gave us is things like a video re-encoding for YouTube, things like this which just run in the background, and today they just migrated to another system. And they said they also tried it for interactive sessions like probably search or mail, and they said it's not working because the downtime during the migration is at least 4 seconds, and this is something then you would notice as a user. So they only use it today for background tasks, or for long-running, not high-priority tasks. CRIU is integrated in LXC, LXDM to migrate containers. It's available in Docker for a long time, and it's available in Podman. On the Podman integration, that's what I've been working on the last couple of years, and sorry. And the Podman integration was kind of a preparation for my work I'm doing right now to get it into Kubernetes. So I started to implement checkpoint and restore first in Podman and then in CRIU as a CRI implementation for Kubernetes. And the code base is similar, so I could learn how to implement it in Podman and then more or less copy it to CRIU. And this is the thing I'm working on for the last 2 years. And this was the preparation for the integration of checkpointing containers into Kubernetes. There is a Kubernetes issue open since 2015 where somebody asks to migrate containers in Kubernetes. And so this hasn't been implemented in the last 7 years. But the things I've been doing lately, we're getting a small step closer to actually be able to migrate a container from one host, from one node to another node. And the way we are currently, or the way we put it into Kubernetes for the 1.25 release is under the name of forensic container checkpointing. The first two links are just the enhancement proposals which were merged, and the last one is the last link is the actual pull request for the implementations in Kubernetes. The thing which made it difficult, the whole implementation, is that we first had to implement it in Kubernetes, and the Kubernetes implementation is rather small, but we needed the CRA API remote procedure calls for checkpointing because the underlying container engines like Containerd and CRIU, they rely on the definition from Kubernetes. So as long as it's not available in Kubernetes, you cannot merge it in the underlying container engines. And so this is why it was important to get it first into Kubernetes before getting it into in the underlying container engine working. For the container engines, Containerd and CRIU, I have pull requests open to implement it, and so and based on these pull requests, my demos later will be shown. I will show later the demos. So the name forensic container checkpointing is, so we tried to find a way to implement checkpointing of containers in Kubernetes without touching too much code. So we try to find a very minimal implementation of container checkpointing for Kubernetes, and the idea was we call it forensic container checkpointing. So the idea is you have a container running on your Kubernetes system, and you think something might not be right with the container, but sometimes you don't want to immediately stop the container because maybe it hides its code or whatever if you stop it, or so you just want to keep it running and analyze it somewhere else. With forensic container checkpointing, you can take a checkpoint of the container while the container is running. You take the checkpoint, the container keeps running, the container never knows that it was checkpointed. You can now take the checkpoint and take it to another system and analyze the container in a sandbox environment. You can start it as many times you want from the checkpoint. You can look at all the memory pages because now you have them on disk. And so this enables you to look at the container in a much more detailed way without touching or changing the actual container that's running on your production system. So you now have all your memory pages on disk. This also means there's a security implication. If you do a checkpoint, all of a sudden, all of the information which was in memory, which may include random numbers, keys, things like this, security things, is now all written on disk. For the forensic container checkpointing, what we currently do is we try to ensure that the checkpoint archive we create is only readable by root. So the assumption is, if you have root on the system, you can access anyway all the memory pages of all processes on your system. And if we write them to disk and it's only accessible by root, then there shouldn't be any additional problem, we hope at least. We didn't introduce anything. So with this, just want to show a couple of use cases. So the most simple use case is what I call a reboot in safe state. So we have a system running a kernel, a blue kernel, and we have a container running on the system. And now you want to upgrade your kernel of the system because there's a security issue with the system. But the problem is your container takes forever to start up because it has a long initialization. It needs to read a lot of data from disk. So what you can do now with checkpointing in not just Kubernetes, but with all the container engines I've shown before is you can take a copy of the container, you just write it to disk, then you reboot your system, so now it's gone, it's just a container on the disk is still there, and then you reboot into the green kernel, and the container is in exactly the same state as before. And this is also where I want to show my demo. So here. So this is a RHEL 8 system, and I want to show this with Podman. The steps down there are all the same that with what would happen later with Kubernetes. So I will just start a container. That's a real simple container. The important thing is it has to be a stateful container. If it's not stateful, there's no reason to checkpoint it. And so this container is a Python server, and it returns a number. It increases it. The second time I talk to it, I get the increased number. So it's really simple, but it's stateful. So I get, I don't know, there's a C, there's counter 0, counter 1, counter 2. So now I can say podman container check point and use the latest container you know of. And if I now try to talk to the container, it doesn't work because it's gone. It's checkpointed. Now I reboot the system. This is a local VM here. Just wait until it comes up. Seems to be up again already. So still doesn't work. Now I can say podman container restore. Also latest container you know about. And then I again connect to it, and now I get 3, 4. So the container was checkpointed. I rebooted. I kept all the state of the container, and now it continues to run where it was before. So this is the most simple use case. So another use case is bit of a combination of the previous one. It's what I call a quick startup. So let's go ahead. So you have a container. Again, it takes forever to initialize, and you want to have another copy of it. And one of the reasons for this use case was at some point when I started to write the Kubernetes enhancement proposal, I was contacted from someone from they had, I think MathWorks. They are doing MATLAB, and they have a MATLAB as a service. And what they do is you can, as a customer, request MATLAB, and then they give you an instance in the cloud somewhere. And what they actually do is, because MATLAB takes like 8 minutes to start or something, that's what they told me. And so what they currently do is they have privileged containers in Kubernetes, and then they start runc in the privileged container to start a MATLAB container. Wait until it's initialized, use the runc interface to take the checkpoint of the container, and then they have a pre-initialized MATLAB container, and once the customer requests MATLAB as a service, I don't know if that's the name, they can start the container from the checkpoint, and then instead of waiting 5 to 8 minutes, they get it up in like 10 seconds. Because the only thing that CRIU or the checkpoint has to do is read all the memory pages back into memory, and then the thing is running again. So all the initialization is gone. And in my diagram, this would look like this. We have, again, a container running. We take a checkpoint. This time, we don't kill the original container because it can keep on running. We can use it for something else. So we create a checkpoint on disk, and then we create multiple copies from the already pre-initialized container, and they will usually start up much faster than if you go through the whole initialization phase your container usually has to go through. So in the demo, this now looks, so we have still our container running here. Yeah. So what I do now is I say podman container checkpoint, I say latest again, and then I say leave running because I don't want the original container to be stopped. Oh, thank you. Leave running, and then I say export because I want to export the checkpoint to an external file, so I can curate copies from it. And leave running latest. I think that's it, yes. And now I can still talk to my container, so it says now 6, 7, 8. And if I now restore the container from the checkpoint, from the external checkpoint, I can say import. And this will fail now, because as default, podman will try to recreate a container with the same ID and the same name. So I'll just tell podman, yeah, I know, use another name. I say counter 1. And I say counter 2, so I have 2 copies now running of it. Podman So this is the original encounter 1, encounter 2. And now I can just talk to all those containers. And I forgot now which one should be which, but let's see. So I say counter 1. So this continues to run from 6, 7, 8. I can use counter 2. Also starts from the same checkpoint. And the original container is called elated Blackburn. This should also work. And this should also give us a 6 now. No, 9. So this was wrong. I took the checkpoint before. OK. So now I have 3 containers running, and 2 are copies from an already pre-initialized container. And so that way I can start up the container much faster if it's stateful and if it takes a long time to start up. And the last use case is the combination of those use cases, kind of container live migration. So we take, we have now 2 hosts, source and destination system. The container's running on one system. We take a checkpoint of the container, write it to disk or somewhere else, and transfer it to the destination and start 1 or multiple copies of it. And this should now use my, my Kubernetes changes. So the VMs were local before, and this is now a VM which is a couple 100 kilometers away. So the SSH session sometimes breaks up. So there's currently no container running on my Kubernetes thing here. So what I have a pod with 2 containers. Both, one is the same container as before. The other one is the same container, but in Java, the Wildfly hello, it's the same thing. It also gives me just a number. So now I will start this pod. Then I will take a checkpoint of the container counter. Then I will copy the checkpoint to a registry. Then I will, on another system, start a similar YAML file. I will then point Kubernetes to the checkpointed container, and then Kubernetes will restore or will start the container from the restored image. And this gives me a kind of migration. It's not really fast because we have to go through a registry, and because it's all manual at this point, but this is still very early, all what we currently can do, but we at least can do it at this point. So let's say apply. So now it should describe pod. So the containers So the container is now running. We have now 2 containers running in Kubernetes here. And I want to checkpoint this one. First, I want to talk to it. So I just need to get the IP address of the container, and then I can talk to it. So I say, again, it's the same container, same port. It gives me, again, counter 0, 1, 2. And I can checkpoint it inside using Kubernetes APIs. So this would work something like this. At this point, it's a kubelet-only API because of the security implications I talked about before. We were not sure yet how to expose it at the kubectl level. So currently, we only expose it at a kubelet API level. So I can request at the kubelet port, I can say I want to do a checkpoint of the namespace default of the pod counters of the container counter. So I do this, and then it just returns me. It has written this this file, and this now contains the checkpoint. For the migration demo, I'm doing a bit differently. I'm using the CRI interface directly to the checkpoint. CRI control check. No, where is it? Checkpoint, and then I have to my SSH session is breaking away. So let's use this container here. So, and I'm writing it to my local image store. I call it localhost/checkpoint image tech 25. So now the checkpoint is written. Now I'm logging into a registry, and now I say podman push tech 25 to tech 25. So now the checkpoint image is pushed to the registry, and now I'm switching to another system. So this is also a local VM. This is now running Fedora 36, and this also has Kubernetes running, I guess. Describe pods. Yeah, so Kubernetes running. And now I will, what did I say? 10 to 5. So it's the same definition again, but instead it has one container is the same, but the other one will be started from the checkpoint. So I'm saying I want to use the image with the tag 25. And now I will tell Kubernetes to start this pod. And now I can say describe pods. No, describe. Describe, or maybe pods. And now it says, it pulled the image from the registry, it created the container, and it started the container. And so now we should have a container from a checkpoint. And let's try to talk to it. Same strange command line. And now it shouldn't return counter 0. I don't know, 3 or 4, something like this. Yeah, 4. So we now migrated a container over a registry, keeping the state of everything. At this place, it was just a single integer. We kept the state, but all the memory pages were part of the checkpoint. So whatever has changed during the time is now also migrated from one host to another host. So this is the last use case. So now I want to talk a bit about CRIU, the lowest level of the checkpointing. So what now happens in Kubernetes is, if you want to take a checkpoint, currently you talk to the kubelet API, then the kubelet will trigger the container engine, containerd or CRIU, to do a checkpoint. The container engine will talk to the container runtime, runc or crun, to do a checkpoint. Crun or runc will talk to CRIU to do a checkpoint. CRIU does the checkpoint, writes it to disk, and then it goes up the stack again, and then the container engine level, so at CRIU or containerd, it will all put it into an image and put the image either to local disk or in the local image store, and then it can be used as a tar archive to transfer it locally, or it can be used to transfer it to registry. And the lowest level here is CRIU. So to migrate a process, we have 2 steps, basically. We do a checkpoint, then we transfer and restore it. So the first step is checkpointing. What happens during checkpointing? CRIU does basically, it pauses all processes you want to checkpoint. So what you do with CRIU, you point it at a PID, and the checkpoint will be done of the PID you point it to and all child processes. You cannot break up parent-child relations during checkpointing with CRIU, so this will always be a tree or one process if it has no child processes. And so we either use ptrace to stop all processes or the cgroup freezer to stop all processes. Once the processes are stopped, we collect all the necessary information from Userspace. We don't never go to the kernel to collect any information and write it to disk. There are basically 2 ways to collect information about a process for CRIU. There's the proc-pit interface. And CRIU started with this interface, and it was using as many of the existing interfaces as possible. And we go through all the information which is there and try to save the state of the process so that it can be later restored. Over the years, CRIU added additional interfaces to the kernel to help make checkpointing easier. All those new interfaces are not only used for checkpointing, they can also be used by other tools. So none of the interface, or almost none of the interfaces CRIU introduced into the kernel are checkpoint restore only interfaces. So once we have collected all the information from PIT, then the next step happens, and this is what CRIU calls the parasite code. The parasite code is injected into the process, and then the parasite code continues to run in the process which we want to checkpoint. This is, it's kind of a daemon, so it runs in a loop and it waits for commands, and then it does what the main CRIU process tells it to do. And the reason for doing it this way is now we can get all the information from the process from within the process's address space, not namespace. So we can see all the memory pages and everything the process can see, and then we can transfer it from within the process to the outside, where the main CRIU process waits for the information and writes it to disk as it gets all the necessary information. The parasite code is removed after usage, and the process never knows it was checkpointed. It never knows it was under the control of the parasite code, and then it just keeps on running, or you kill it, whatever you want to do with your process at this point. I tried to create a little diagram here. So this is the original process code to be checkpointed. We take one part of the code out. We replace it with the parasite code. Now the parasite code is running inside of the address space of the process. And later we restore the original code, and the process never knows it was checkpointed. At this point, checkpointing is finished. All information has been written to disk. And as already mentioned, the target process can be killed, or it continues to run. We've seen both things in my demos. Once we killed it, once we kept it running. So this is really up to what you need. So to restore, this is the second or last step of the migration, is CRIU usually reads in all the checkpoint images, and from this information we try to recreate the processes as they were before. As already mentioned, the process tree is recreated as it was before. This means all PIDs stay the same. This also means that if you are running not a container, then there's the possibility of a PID collision, because if the PID already exists, then CRIU cannot create the process tree as it was. For the container use case with PID namespaces, this is not a problem, because only the PID inside the PID namespace needs to stay the same. The PID outside of the PID namespace can be whatever it is. We used to do this with clone system call before. This was a bit more complicated because clone does not allow you to specify which PID you want. With clone 3, you can tell the kernel, okay, I want a process with this PID, please create it for me. This just makes it easier for us internally. Yeah, that's how we recreate a process tree. And then once we have the process tree, we have a copy of a lot of CRIU processes, and then those processes are morphed into the original processes. And the file descriptors are always a very good example, I think. So during checkpointing, we look at all open file descriptors. So we see file descriptor 5 points to this file and this position. We remember this in our checkpoint images. And on restore, we open the file again, change the file descriptor to 5, and put the file position pointer at the same location as it was before. And once the process continues running, for the process, it would look like as the file descriptor is the exact same thing as before, although we just manually set it up to point it to this location. And that's how we do it with all the resources CRIU can manage. Or basically, that's the idea behind the whole thing. And then we map all the memory pages back into the right locations. We load all security settings like AppArmor, SELinux, seccomp. We do this very late because the security settings would sometimes block things we would like to do with CRIU. But the podman thing was completely SELinux enabled. I don't remember if I'm doing it for Kubernetes already, but we're restoring all the SELinux labels as they were before. So the labels are there. So you have the same confinement as before from SELinux and seccomp. And once we have reformed everything as it was before. We jump into the restart process, and it just continues to run without ever knowing it was checkpointed. So this is the thing about CRIU, the low-level thing. And so just a bit about what we want to do next in Kubernetes. So at this point, we can kind of migrate using checkpoint, push it to a registry, then trick Kubernetes by using the create start command on a checkpoint image to believe it's a new container. So we can kind of migrate, but this is only the start. So this was the first step, what we wanted to do. So the next thing is maybe kubectl checkpoint so that we can checkpoint a container at a kubectl level. The problem is we haven't yet completely discussed how to secure this enough so that not anybody can just create a checkpoint and get access to all the memory pages. So this still requires a lot of discussion around securing this correctly. And then we thought about creating a separate restore command at some point, but at this point we probably always go through create and start, and which is, at least in Podman, is the combination of run. So maybe this is the easiest thing to do and just take out the complexity at the Kubernetes level. Then the next thing would be pod checkpoint restore. So this already worked in one of my proof of concepts. This is, in the end, it's pretty easy. I just loop over all the containers in a pod, checkpoint them all, include some metadata for the infrastructure container if there's one, and then I can easily restore it without a problem. We haven't discussed this as part of the current cap and code which was merged into Kubernetes. The thing is, I don't have an idea yet how to restore a pod easily, because I cannot, without changes, I think, at the pod YAML level, tell Kubernetes, start the pod from this image. This doesn't exist, so we need to find a way how to restore a pod. Or we need to find the right place where a user can specify this. Another idea is then, if this all works, we can maybe talk about something like kubectl migrate, to migrate a running container from one system to another without going all the manual steps I've just done. And if this all works, at some point, maybe we can have a scheduler integration where the scheduler decides, okay, at this point, resources are low, I have this low priority pod container running here, maybe I can move it somewhere else without impacting the currently running high priority tasks on this node. And with this, I'm already at the end. So the summary of my presentation is CRIU can checkpoint and restore containers. It's integrated in different container engines, runtimes, orchestrations already. It's used in production systems. The use cases I've shown is reboot into new kernel without losing container state, start multiple copies of a pre-initialized containers faster, migrate running containers. I've talked about a forensic container checkpointing cap, how we currently introduce checkpointing into Kubernetes, and the restore is currently going via run, which is a combination of create and start, I think. And with this, I'm at the end, and thank you for your time and attention, and happy to answer any questions.